Thank you. First of all, I would like to thank the organizers who invited me for this very focused workshop on vortex particles. I am from India, from the Birla Institute of Technology and Science. Is one of the premier engineering and science institutes of India. And I will be talking about on the vortex electron collision with atomic and molecular targets. So I suppose that most of the talks are related to vortex photons. So I am a bit orthogonal to vortex photons, but anyways, vortex is common here. So starting with the introduction and then theoretical formalism, results and discussion, conclusion, more or less I will go with this way. So let us talk about the conventional versus photon beams. So conventional photon beam carry spin angular momentum related to polarization, but twisted photons beam carry orbital angular momentum. As you have, we have two talks before my talk, and we have talked a lot about this orbital angular momentum. So this is the way we can describe. This is plane wave, and there is featureless if you look at the phase part, and this is the twisted photon where we have this helical phase. And so starting from the historical point of view, Aaron predicted that the light can have an orbital angular momentum, and this can be a free particle, a free beam. And of course, after that, there are so many activities in the literature, and I am just quoting this article by Allen in 1999. So it's just a historical point of view. Started with the mechanical aspect of this light, which exert a torque, and this is purely from the circular polarized light discussed by Poynting in 1901, and this is an extract from the this article, which talks this conclusion part. This extract is from the conclusion part. So it discusses a very few years old this literature, and of course at that time he's in this article he concluded that whatever discussed in the article is very rich, and it's just starting, and yet to be discovered in this year to come concerning the full properties and relationship to spin, this angular orbital angular momentum aspects. And after this, cited 99 till 2026, so more than 2.5 decades, a lot of activities have been done, and of course the activity we are here for this workshop is also related to this field. So Gabriel discussed various aspects of course in many articles this has been reiterated that its application to various fields like biophysics, micromechanics, microfluids, the optical data storage, quantum communications, and of course the previous talk talks about the possibility in quantum technology and many more aspects. So it's a very, very rich application of the vortex photon beam. But I will not discuss about the twisted photons. Here I will be discussing about the interaction of twisted electrons with the atomic and molecular target. So as mentioned earlier, for twisted photons, we can distinguish the conventional electron beams which carry the spin angular momentum related to their polarization, spin up, spin down, or longitudinal with helicity and so on. We can describe this intrinsic angular momentum. But when we talk about twisted electrons beam, it carry orbital angular momentum along the propagation direction in addition to spin angular momentum. So twisted electrons beam have a transverse spatial profile and their corresponding transverse phase depending upon OM. So this picture, thanks to this article, I use this picture. This L equals to 0, as you can see, is a very localized Gaussian type. So the intensity distribution is localized here. And if you look at the phase, it's featureless. But if you look at the twisted electron beam, then as you can see that the intensity is unevenly distributed, and especially at the beam axis, the intensity is 0 and the phase is indeterminate. While if you consider the phase, as you can see for L equals to 1 and L equals to -1, the phase changes from 0 to 2 pi, that's a full rotation, so L equals to 1. But if you consider L equals to 2 and L equals to -2, you can see that the phase changes twice in 2 pi rotation, and L equals to 3 and so on. So the phase as well as the intensity profile is completely different from the plane wave. So it has a spatial structure. So let us talk about the genesis of electron beam from the experimental point of view. So there were 2 papers in 2010 in Nature, and they reported the generation of electrons being carrying orbital angular momentum, electron vortex beam. So this is the way you can describe the phase structure when it propagates. So it's one full rotation, the phase rotates with full, but if you consider full rotation, the phase rotates twice in this case, and in this case 3 times. So of course from layman point of view we can describe this vortex in general is like this. There is a vortex here and there is the intensity is 0 on the beam axis, and this is the way the phase changes. As you can see for m equals to 1, the phase covers 0 to 2 pi, but if you consider m equals to 3, you can see that this and this, so these are identical phase, 1, 2 and 3, so 3 times the phase changes in 2 pi rotation. And this is the way we can describe from this article, I am using this. The plane wave, the current goes along this rectilinear direction and the phase is with this, what is this color? I think kind color, and the phase is constant. If you consider the vortex being for L equals to 1 and -1, as you can see that the current goes this way, so it's like this way, and of course the phase changes like this, as I mentioned earlier also. So let us talk about what my group has done in last 6 years related to this the application of twisted electron with a fundamental point of view, that how does this twisted electron beam interacts with the atomic and molecular target. So we have a lot of studies in atomic and molecular physics where we use conventional electron beam and just consider its interaction with the atomic and molecular target. So let us revisit these processes. Only thing is that we just replace this conventional beam with the vortex beam and look at the contrast results we get when we consider this vortex beam. So this is the way, of course this is most complete kinematical picture in the sense that this is for a twisted electron impact ionization, but I can also describe the elastic scattering and other processes through this picture. So along z direction we have this the propagation of incident beam, and as I discussed earlier that it carries angular momentum and the phase as well as the intensity and the plane perpendicular to propagation vary. And there is a target here, so a target can be on the axis or can be off the axis. Off the axis can be described with the phase related to impact parameter B. And of course, if we consider just elastic scattering part, then this incident electron is scattered in this direction, let us say Ks, fine. So what we studied here is that we have an incident beam which is twisted beam, and it can have any angular momentum. Mainly in our study we take 1 and 2 and 3, and with this interaction it imparts some angular momentum, but we are not bothered what happens to this this orbital angular momentum. We assume that okay, there may be some detector which can detect only plane wave rather than the vortex electrons. So this scattered electron we describe as a plane wave, and the incident electron as a twisted electron. There is other possibility that it may lead to the ejection of one of the electrons. So Ke represents one of the electrons. So if it is 1s this hydrogen target, then you have electron in 1s orbital, and that electron is ejected, and this will be better. The scattered and ejected electrons are detected coincidentally. So this coincident this detection of 2 electrons started way back in 1969, and 1969 onwards there are many theoretical and experimental studies where this coincident detection of scattered electron and ejected electron are studied. So coincident detection means both the scattered and ejected electron are detected with their momenta fully resolved, right? So this is the key, that their momenta are fully resolved, they are fully controlled. So in the way that one can change the scattered angle, one can change the ejected electron angle, one can change the energy of any of the electrons, and can probe the ionization process. So we have a lot of kinematical domains where we can study the electron impact ionization process, and we can learn about the ionization process. So in a way it gives complete picture of the single ionization process except spin. So this is the time capsule of vortex electron matter collision. So the Bliok, I think, is somewhere here. I don't know whether he is here or not. Yeah. So I am recording his it's a very beautiful article, physics reports, Lloyd et al. Same time, 2017. And there are many more articles. So I don't want, it's not a complete list, and just for a representation I am giving this picture. And what about E2E collision? So as I mentioned earlier that we have a rich history for conventional E2E process, but the E2E process with twisted electron beams theoretically started recently. In 2020, Harris et al. Reported E2E collision on hydrogen atoms. Subsequently, the same group also reported in 2023, and recently in 2025 also. And also Gong et al. Reported E2E on H2O. And of course, there are a few papers from our group, we have studied twisted electron beam E2E process. So this is already discussed this part. So the motivation is clear, and as mentioned by my two predecessor speakers, that the vortex beams have a rich future prospects. We can revisit many basic processes at atomic or subatomic level, and we can get more information using this vortex beam. And of course, there are many interesting results have been shown in these articles. So we have the additional degree of freedom when we talk about this vortex electron collision, this angular momentum. So we can play with this orbital angular momentum, and we can get more information as compared to the conventional electron beam collision. So let us talk about the twisted electron beam. So it has a helical phase, and while it's propagating, it goes this way. So naturally, it has a cylindrical symmetry, so we use cylindrical coordinates to describe. So this EIKZ is just a plane wave, like a plane wave. So it's just a plane wave component of orbital this vortex beam. So it just go this way linearly, and the square of this represents the intensity in the transverse plane, and this represents the helical phase e to the power I m5. So this depends on m. But normally for our calculation we use the momentum space representation where this twisted electron beam with particular angular momentum can be described as a superposition of plane wave, and this represents the amplitude of the given plane wave, and finally it can be rewritten like this. So this EIK perpendicular dot r is the perpendicular momentum part, and this is the amplitude related to this, and we use this. And of course, as I mentioned in this picture, that if you want to describe this vortex electron beam in momentum space, then it can be described on a cone with this angle is nothing but the opening angle of the beam, and as this beam propagates along this direction, so this beam twists around this, and the net momentum is along this, which is, you can say that it traces on this conical surface, right? So you can decompose this vector ki along z axis and along perpendicular axis, and you can describe this as the x component, y component and z component, and the momentum transfer can be given as ki minus ks and can be written in terms of this theta, and this theta is in terms of the opening angle of the vortex electron beam, and phi p and phi s, phi is this represents, phi s is for the scattered electron and phi p is related to the phase of the twisted electron. So one of my PhD students role is here. So here's a poster, yeah, you have poster, which will describe the twisted electron scattering on CO2 molecule. So this is a CO2 molecule, and let us assume that it is at a distance b, described by this impact parameter. So this is the way the beam is propagating, and this is the momentum of the beam, and this makes theta p angle, which we call opening angle, and the perpendicular component, it rotates because of the angular momentum, it rotates, and phi p is the phase of this perpendicular momentum from down the x-axis. And these are the results, very interesting result, that if we go with the twisted electron beam, then we have a sharp peak when the scattering angle, so it's just elastic process, the incident beam is scattered by some angle, and we are varying this angle, and we are looking at the cross section as a function of the scattering angle. So it's the angular distribution of the scattered electron. So we have a sharp peak when the scattering angle is equals to the opening angle, while for the other cases the cross section is small, and the solid light represents the plane wave calculation. So as you can see that when we move from plane wave to twisted electron beam, we have a different feature, especially the sharp peak when theta s equals to theta p. So for all ml or orbital angular momentum, we got the same result, and of course experimentally it is very difficult to precisely locate the atomic target at some point. So experimental realization is that you just integrate over all the impact parameters, and the cross section, when we integrate over all the impact parameter, is just for macroscopic targets. So in that case, experimentally it is more convenient to have this twisted electron study on macroscopic target. So for macroscopic target, when we consider, in that case, the orbital angular momentum part is washed out when we integrate over impact parameter. So the cross section depends only on the opening angle of the twisted electron beam. So as you can see that for 6 degree we have the sharp peak, for 20 degree and 45 degree, on all cases we got the peak when the scattering angle is equal to the opening angle of the twisted beam, while for other case the cross section is small, and there is a sharp contrast with the plane wave result. So let us discuss about the E2E process. So in the E2E process, in the elastic scattering, we assume that this twisted electron beam is propagating in this direction, and we rotate this Ks and we find out the cross section and we look at the angular distribution of the cross section. While in the ionization case, we assume that one of the electrons of the target is ejected, let us say hydrogen atom for simple case. So the ejected electron and the scattered electrons are detected coincidentally, but that means their momenta is fully resolved. So this is the way cross section can be found, as technically not possible to describe everything right now. So let us look at the result. The solid line represents the plane wave results. So this is the triple differential cross section for neon target. So I am assuming that I have a neon target which is on the beam axis, and the ejected electron carries this energy while the incident energy carries this, and the scattering angle is 6 degree. So let us look at this part. When there is no angular momentum, that means the plane wave, we get one peak in the binary direction, that is momentum transfer direction, and another peak is in the recoil direction. So just a recoil of the ion which leads to this big peak. But if you consider theta p equals to 6 degree, then we do not get binary and recoil peak. We get a forward peak and a backward peak. So there is a drastic change in the angular distribution when we consider twisted electron beam instead of plane wave. And that is also true for m equals to 1, m equals to 2 and m equals to 3. Fine. And this the right one shows the TDCS for the microscopic target. So this is plane wave and this is theta p equals to 1 degree. That means the opening angle of the beam is very small. So in that case, the angular distribution mimics like plane wave. But if we increase the opening angle, in that case we can see the drastic change. So theta p equals to 6 degree, we get a forward peak and a backward peak. But in plane wave, we get binary peak in the momentum transfer and recoil peak in the opposite to momentum transfer. So there is a drastic change in the angular distribution of, and that is true for other cases also. These also, we also discuss, how much time do I have? 3 minutes, okay. So we have also discussed the E2E collision on heavy target AG, and we use this semi-relativistic E2E studies for this, and the cross section this represents for conventional plane wave, and the others represents the cross section for different orbital angular momentum. As you can see that there is a drastic change in the angular distribution of twisted electron beam when we compare with the conventional plane wave. This we also discussed for hydrogen molecules. So the earlier case is atomic target. Now hydrogen molecule is very important because it behaves like two identical scatterers. So it's like a double slit if you consider that quantum level, and we can see the interference aspect, but I can't show here because I just want to see that how the plane wave results are contrasted here when this twisted electron beam is used. So the black curve is just a twisted this plane wave cross section. So we have a binary peak and recoil peak. Theta s equals to 1 degree, but when we take different angular momentum, as we have seen that we have a predominantly a forward peak and a secondary peak in the recoil direction. So this is a contrast result, and this is for the microscopic target. So we have a binary and recoil peak, and as we can see that when we change the opening angles, we have a different results. So it's not possible to describe all the things here, but the bottom line is that when we replace the conventional beam with the vortex beam, there are a lot of different features we can observe. And we have also extended for this E2E collision on water molecule. So this is 1b2, it's a p-like orbital. We get this plane wave results, and as you can see that when we consider the twisted electron beam with different orbital angular momentum, we have different features, predominantly as observed earlier, the forward peak and the recoil peak, and that is also true for other orbitals for H2O, and this is for microscopic H2O target. And the last part of the talk is we also discussed the laser assisted E2E on atomic target. So earlier we studied this E2E with electron incident on atomic target, and we have a scattered electron and ejected electron, and they are detected in coincidence. Now in this study we include laser, but the laser with weak field in the sense that laser field is not sufficient to ionize the atomic target, it's just perturbation to the E2E collision. And we have seen that this is the plane wave result, the solid curve. So predominantly we have a binary peak, and when we include this twisted electron, we have this peak in the backward direction and in the forward direction, and this is laser assisted plane wave. So this dotted red line is laser assisted plane wave. Okay, and this is for different targets, and we have seen that the effect of twisted electron beam. And the last result of my presentation is this laser assisted on H2O molecular target. This is the plane wave result, and of course we have the two different degrees of freedom here. One is the polarization of laser field, plus the additional degree is the orbital angular momentum of the incident twisted beam. So what we did, we choose the polarization along the incident direction, perpendicular to incident direction, perpendicular to momentum transfer, and parallel to momentum transfer. And we have seen that when we consider laser effect, then we have multiple peaks. But what about the plane wave part for this 2A1 orbital? So laser assisted case we have multiple peaks, but for the plane wave we have just this. So there is a significant aspect of laser assisted process on this process. So the cross section for vortex electron collision are highly contrasted with that of the plane wave collision. I have shown some results where you can appreciate that there is a contrast result when we replace conventional electron with the twisted electrons. The field of electron or photon vortex beams is rich and has a bright future, as mentioned by earlier two speakers, and the speakers who will be talking after me for today and next 1.5 days. This may initiate the experimental works on this process. Experimental work have been reported, but for this case, this scattering and E2E collisions, it may lead to this. The study at the atomic level will definitely have application in other fields, material science, optical. So basically we are discussing this, the interaction, the scattering problem. We are revisiting scattering problem with the twisted electron beam on atomic and molecular targets. And once we get sufficient information at basic atomic and molecular targets, it can be expanded to other field. The study of twisted photons. Now there is the important field where one can discuss the twisted photons and twisted electrons. So when you consider twisted electrons in a low momentum transfer conditions, so in that case it behaves like a photon because it impart very low momentum to the target. So in that case we can study the similarity and contrast between the twisted photons collision and twisted electrons collision. That may be explored. These are our current publications in last 4 and 5 years, mainly in Journal of Physics B and Physical Review, and these two are on archive, the latest results. I would like to acknowledge DST ANRF for funding, and Roel was the research scholar of that funding. And now he is still my PhD student, but on different funding. Of course, my institute BITS Pilani, without money nobody can travel. So I got traveling funding from my institute, and thanks to organizers for extending the local hospitality. So organizers of SPICE workshop, last but not the least research scholar of my group and collaborators. So one of my research scholars' role is participating in this workshop, and he will be presenting a poster tomorrow. Okay, and he is one of the co-supervisors. I am his supervisor. One of my co-supervisor is Jan Minar. Somewhere Jan Minar is here. Yeah, and the other co-supervisor, his co-supervisor Didier CHOUBISA was supposed to come for this conference, but because of some very unfortunate incident, he was not able to come. So in a way, for me, it's a great day for Roel also, that his supervisor, co-supervisor, and himself is attending this conference. This is my group. So this is Didier CHOUBISA, who was supposed to come and couldn't come. And thank you for your attention.